In this video, we discuss the Heisenberg Uncertainty principle and its more general form. The central quantity for the uncertainty principle is the standard deviation. Or root mean square deviation, RMSD, or simply uncertainty. The standard deviation, sigma A, of a set of measurements of an observable A, represented by an operator A hat, is given by the square root of the expectation value of A hat minus expectation value of A, all of its squared expectation value, and the square root of that. Or, in a more simple fashion, the square root of the expectation value of A squared minus the expectation value of A squared. This second expression is easier to calculate. Here, we imply the given state psi. Sigma A is sometimes denoted as delta A, which is a little more ambiguous as a notation. Now, what is sigma A? Sigma A is essentially the root mean square error of a set of measurements. It characterizes the scatter you get when measuring A on a set of identically prepared systems. It's zero if all the measurements give the same result, and a positive number otherwise. Let's now look at the general uncertainty principle. It relates the standard deviations of two observables, sigma A times sigma B, larger or equal to 1/2 the magnitude of the expectation value of operator C, where C operator is equal to the commutator of operator A and operator B. It says that no matter what state psi of the quantum system is, that the product of the standard deviations, or uncertainties, of the measurements of A and B, of two observables A and B, sigma A times sigma B, cannot be lower than a certain limit that is determined by the state and the commutator of the two observables. More practically, let's say you prepare 1,000 boxes, like 1,000 quantum systems, or boxes with one particle in each in the same state psi. Measure A on 500 boxes. And you will get some average or expectation value A with some scatter or standard deviation sigma A. Now you do the same on the remaining 500 boxes with observable B. You get some average expectation value B with some scatter sigma B. Now we need to distinguish two cases. First, if A and B don't commute, we say the two observables are incompatible. And the uncertainty principle says that there is a positive lower limit on the product of the two standard deviations. The right-hand side is a positive number. In this case, the product of the two measurement uncertainties cannot both be zero at the same time. In other words, there is no state whatsoever for a particle in a box where we can get well-defined results for both A and B at the same time. On the other hand, and this is the second case, if the two operators commute, commutator of AB equals 0, the right-hand side in the uncertainty principle is 0. A and B are said to be compatible. Some states are possible where the uncertainties in the measurements of A and B can both be 0, so that both measurements give well-defined result without any scatter. In essence, the uncertainty principle tells us about the statistics of measurement. Let's look at an important specific case, where A is the position x and B is the linear momentum along x, px. The commutator of the two is x px equals I h bar. Let's insert this into the general uncertainty principle. We get sigma x times sigma px larger equal to 1/2 h bar for any state psi. In different notation, delta x times delta px larger equal 1/2 h bar. Clearly, the x position and the linear momentum along x are incompatible. This is called the Heisenberg uncertainty principle. It means that there are no states whatsoever where you can determine the position and the momentum of a particle precisely at the same time. This principle can be illustrated in the following way. Remember that the momentum and the wavelength of a particle are related by the de Broglie relationship, lambda equals h over p. Take a wave function that looks like a regular wave. It's clear that it has a fairly well-defined wavelength. So lambda and the momentum are fairly well defined. But asking about the position of this wave would not make any sense. The wave is everywhere and the position is not well defined at all. On the other hand, look at the wave function that looks like a single spike. Now talking about the wavelength or momentum doesn't make any sense. It's not well defined. However, you can make a reasonably accurate statement about the position. This illustrates the Heisenberg uncertainty principle. The more accurately you can determine the position, like in the second case, the less accurately you can get the momentum, and vice versa, which has been shown in the first case. It is impossible to have a particle in a state where both its position and its momentum can be determined with infinite precision. Of course, the Heisenberg uncertainty principle is an inequality, so you can have states where neither the position nor the momentum can be obtained accurately at all. Just draw a squiggly line like this. Here, the product of the two uncertainties is large. Neither the position is well defined, nor the wavelength or momentum. On the opposite end, there exists a state that looks like this. This is a unique state where the inequality becomes an equality. This is called a minimum uncertainty state. This has the general form of a Gaussian wave function.